Good morning, one and all. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in today's lecture, we are going to learn about definitions in Module 2, that is Magnetostatics in electromagnetic waves and transmission lines. So, first, there are two major governing laws in magnetostatic laws, as one is Biot-Savart's law and the next one is called Ampere's circuit law. So, the first, Biot-Savart's law. The first question is given us here. State Biot-Savart's law. Means it states that the magnetic field intensity H produced at a point P by the differential current element IDL is proportional to the product IDL and the sine of the angle between the element and the line joining P to the element and is inversely proportional to the square of the distance between the point P and the current element as IDL. Right? So, Biot-Savart's law states that it deals as the differential component of magnetic field intensity as dH. So, it states that magnetic field intensity H bar produced at a point P by the differential current element, means generally current is denoted with I and differential current element means it is represented with IDL and is proportional to the product IDL and the sine of the angle between the element and the line joining P to the element and is inversely proportional to the square of the distance between the point P and the current element as IDL. Means DH is directly proportional to the IDL into sine alpha by R square. Right? So, differential component of magnetic field intensity DH is directly proportional to the product of current element IDL and the sinusoidal angle between the current element IDL and the point P, and it is inversely proportional to the square of the distance between the current element IDL and the point P, where we are going to evaluate the magnetic field intensity. Right? So, this is what Biot-Savart's law. So, Biot-Savart's are two scientists' names who proposed the differential component of magnetic field intensity, which is analogous to Coulomb's law in electrostatic fields. Next, define Ampere's circuit law, where Ampere's circuit law states that the line integral of the tangential component of H. Line integral means integral L of the tangential component of H around a closed path is the same as the net current enclosed by that path. Means Ampere's circuit law states that line integral of the tangential component of H means integral L H dot dl, where H is a vector, dl is also a vector. So, Ampere's circuit law states that the line integral of the tangential component of H around a closed path is the same as the net current enclosed by that path. Means I enclosed is equal to integral L H dot dl. Right? So, one of the Maxwell's equation which is to be derived in magnetostatic fields is nothing but that is from Ampere's circuit law. It states that the line integral of the tangential component of H around a closed path. So, closed line integral L H dot dl is equal to I enclosed, where net enclosed means this I enclosed can be given in terms of current density as integral S J dot ds. Right? So, these are the two important laws which we will study in magnetostatic fields. Biot-Savart's law and Ampere's circuit law, where this Ampere's circuit law is analogous to the Gauss law in electrostatic fields. Right? So, Biot-Savart's law states that means it deals with the magnetic differential component of magnetic field intensity and it is directly proportional to the product of current element IDL and the sinusoidal angle alpha between the current element IDL and the point P, and it is inversely proportional to the square of the distance between the point P and the current element IDL. So dH is directly proportional to the IDL into sine alpha by R square, where the proportionality constant is replaced by K and it is given by K equal to 1 by 4 pi. Now, Ampere's circuit law. To define this Ampere circuit law and in order to derive one of the Maxwell's equation for the magnetostatic fields, we need to know first definition or statement regarding this Ampere's circuit law. So, it states that the line integral of the tangential component of H around a closed path is the same as the net current enclosed by that path. That is, closed line integral means integral L H dot dl is equal to I enclosed, where I enclosed is equal to integral S J dot ds. These are the two important laws which we will learn in this particular module 2 as magnetostatics. Next, define magnetic flux density. So, in order to define this magnetic flux density, first flux means number of lines of force and magnetic flux means magnetic lines of force and density means per unit area. Means this can be denoted with or defined as magnetic flux density. B is defined as the force per unit current element. That is given by here B bar equal to mu into H bar. Right? So magnetic flux density is denoted with B bar and it is given by in terms of magnetic field intensity as B bar equal to mu into H. The magnetic field B is defined as the force per unit current element and generally it is measured in Teslas. Or magnetic flux is generally measured in Webers and it occupying some area means magnetic flux per unit area is given by magnetic flux density and sometimes it is to measure in terms of Weber per meter square. Next, what is Lorentz force equation? So Lorentz force is the force experienced by the test charge. The force which is experienced by the test charge is represented with Lorentz force equation and it is maximum if the direction of the moment of charge is perpendicular to the orientation of the field lines. Right? So it is given by Lorentz force equation, that is F equal to Q into E plus U cross B. Okay. Related to the means this to define this Lorentz force equation, we need to consider the force related to the electrostatic fields as well as magnetostatic fields. The force related to electrostatic fields means Fe is equal to Q into E, and the same charge, if the stationary charge is moving with a velocity U, then the field is said to be magnetostatic field. The force experienced related to the magnetic fields is given by Fm and it is given by here Lorentz force equation by combining electrostatic force as well as the magnetostatic force, then that is F bar equal to Q into E plus U bar cross V bar. Right? So Lorentz force is the force experienced by the test charge and it is maximum if the direction of the moment of charge is perpendicular to the orientation of the field lines. Then state Lenz law. Lenz law states that the induced EMF in a closed circuit produces a current which opposes the change in the magnetic flux producing it. That is given by, see, Lenz law means it is defined as it states that the induced EMF in a circuit produces a current which opposes the change in the magnetic flux which is producing within it. Is defined as Lenz law. So, in this particular one, we have learnt the magnetic flux density. In general, it is denoted with V bar and flux density V bar in terms of H bar is given by V bar equal to mu into H bar and generally it is measured in Weber per meter square. So, magnetic flux density V is defined as force per unit current element. And sometimes it is to measure in terms of Teslas also. 1 Tesla are equal to 1 Weber per meter square. Magnetic flux per unit area is given by magnetic flux density and it is represented with V bar. Then what is Lorentz force equation? Means it gives us the combination of both electric field force as well as magnetic force. The combination of those two is said to be Lorentz force equation, and mathematically we can write that equation as F bar equal to Q into E plus U bar cross V bar. Lorentz force is the force experienced by a test charge, and it is maximum if the direction of the moment of charge is perpendicular to the orientation of the field lines, magnetic field lines. So that is given by here F bar equal to Q into E bar plus E bar cross V bar. Right? Applied electric field is E and U be the velocity of an electron and V bar be the magnetic flux density. Then combination of electric force as well as magnetic force gives us Lorentz force equation. Then Lenz's law. It states that the induced EMF in any closed circuit produces a current which opposes the change in the magnetic flux producing within it, said to be Lenz's law. Next, define transformer EMF. The EMF produced by the time varying current that is producing in the time varying B field in a stationary loop is often referred to as transformer EMF in power analysis. So, in order to define this transformer EMF, we need to know the Faraday's law, that is, induced EMF in any closed conducting circuit is directly proportional to the time rate of magnetic flux linkage factor, that is, VEMF is equal to minus d lambda by dt. Here lambda be the magnetic flux linkage factor and it is given by lambda equal to n into psi, where n be the number of turns in the coil and phi be the flux through each turn. Okay, so the induced EMF in the time varying current producing the time varying V field is in a stationary loop is often referred to as the transformer EMF in the power analysis. That is given by here VMF is equal to minus d lambda by dt. Okay? Where lambda be the magnetic flux linkage factor and it is given by n into psi. Then next, define magnetic boundary conditions between two magnetic media. So the normal components of flux density V is continuous across the boundary and the tangential component of field intensity is continuous across the boundary. So the two boundary conditions in the magnetic fields are given by B1n is equal to B2n and H1t minus H2t equal to K. Or for a surface current density is the charge of free of currents, means if K equal to 0, then H1t equal to H2t. Right? So these are the two boundary conditions which we have learned in the particular case of magnetic fields. See, the tangential components of both the magnetic field intensities are continuous across the boundary and the normal components of both the flux densities of medium 1 and 2 are continuous across the boundary. So the normal components of flux density B is continuous across the boundary and the tangential component of field intensity, that is magnetic field intensity, is continuous across the boundary if the boundary is free of current case. Then if it is exist, then H1t minus H2t equal to K. Then if K equal to 0, H1t equal to H2t. Right? So from this, we have learned the transformer EMF and the magnetic boundary conditions. According to this, in order to define this transformer EMF, we need to know first what actually Faraday's law. From the Faraday's law, we will define two types of EMFs, as one is stationary EMF called transformer EMF and another one is called moving EMF, that is motional EMF. Whereas in order to define this transformer EMF, we need to consider stationary loops. So the EMF produced by the time varying current producing the time varying B field in a stationary loop is often referred to as a transformer EMF in the power analysis. And it is given by VEMF is equal to minus d lambda by dt and BEMF is said to be induced EMF in any closed circuit, and it is directly proportional to the time rate of decrease of magnetic flux linkage factor. Whereas that magnetic flux linkage factor is given by lambda and it is represented with n psi. Then define the magnetic boundary conditions between two media. So, in order to define this, the boundary conditions which are exist in the magnetic fields, those are related to the normal components as well as the tangential components. So, first B1n is equal to B2n stands for the normal components of magnetic flux densities in the medium 1 and 2 are continuous across the boundary, and tangential components of both the field intensities, those are H1t and H2t, are continuous across the boundary. Then, what is conduction current density? So, in order to define this current density, we need to know what actually first conduction current density. We need to know how we will define this current density from this conduction current density. So, current is generally measured in flow of charge or flow of electrons, and it is given by current density means current per unit area. Now, in order to define this conduction current density, see, if the amount of current means flow of charges flowing on the surface of a conductor means depending upon the conduction band in a time t, then this surface is always parallel to the current flow. So what is conduction current density? That is given by, notation is given by J, and it is given as mathematically, we can write the equation for that as J is equal to sigma into E bar, right? It is the amount of current flowing on the surface of a conductor in a time t. So that is given by, and here the surface is always parallel to the current flow. The mathematical equation for this is given by J is equal to sigma into E bar, and it is also called as point form of Ohm's law. It is analogous to the normal Ohm's law as V equal to IR. Right? V is nothing but here E, and I is nothing but J, and R is belongs to that sigma. Right? Resistance is and represented with R, where sigma be the conductivity. Okay. Then, what is conduction current density? Means from the conducting medium, we will define this conduction current density depending upon that the ideal value of the conductivity of the conductors is considered to be as infinite. Next, what is displacement current density? So it is defined as the time rate of change of electric flux density is given by displacement current density. Generally, it is represented with JD, which is equal to dou D bar by dou T. See, displacement current density is defined as the time rate of change of electric flux density. Time rate of change of means dou by dou T of, and the change need to be considered in electric flux density, that is represented with D bar, where this D bar can also be called as electric flux density, is also called as electric displacement. Okay, what is conduction current density? Means in order to define current densities, there are three cases. One is JC, and another one is JC, third one is JD. This JC and this JC requires, where first JC requires convection current density, and it is given by rho V into U. Volume charge density, and U be the velocity of an electron. And conduction current density JC is given by sigma into E bar, whereas dou D is called as displacement current density, and it is given by dou D bar by dou T. Okay, so depending upon this, we have learned three types of current densities. One is convection current density, and another one is conduction current density, followed by displacement current density. So now to define this displacement current density is given by statement time rate of change of electric flux density is given by displacement current density, and is to be added in the case of modified form of Ampere's circuit law, and it is one of the Maxwell's equation to be derived in electromagnetics. Next, distinguish between solenoid and toroid. Right? So Solenoid is a cylindrically shaped coil consisting of a large number of closely spaced turns of insulated wire wound usually on a non-magnetic frame. Whereas if a long cylinder solenoid is bent into the form of a ring and thereby closed on itself, is become a toroid. Right? There is difference between the solenoid and toroid, and it is given by here. Solenoid is a cylindrically shaped coil consisting of a large number of closely spaced turns of insulated wire wound usually on a non-magnetic frame, whereas if a long solenoid is bent into the form of a ring and thereby it is closed on itself, it becomes a toroid. This is what the fundamental difference between solenoid and the toroid. Let's define Faraday's law. So this Faraday's law is the one of the Maxwell's equation which is to be considered in time varying waves in electromagnetic waves and transmission lines. So it states that Faraday's law states that the EMF in any closed circuit is equal to the time rate of change of magnetic flux linkage by the circuit. That is given by V EMF is equal to minus d lambda by dt is equal to minus n into d psi by dt. Right? So Faraday's law states that EMF in any closed conducting circuit, that induced EMF is represented with V EMF, is equal to the time rate of change of magnetic flux linkage by the circuit, where this magnetic flux linkage factor is represented with lambda and it is given by n into psi. Right? So magnetic flux linkage factor is represented with lambda and n be the number of turns in that particular coil and psi be the flux through each turn. Right? So distinguish between solenoid and toroid means how will you identify the given one is solenoid type or toroid type means solenoid is a cylindrically shaped coil consisting of a large number of closely spaced turns of insulated wire wound usually on a non-magnetic frame, and if a long cylinder solenoid is bent into the form of a ring and thereby closed on itself, it becomes a toroid. Yes, now to define this Faraday's law, we need to know first induced EMF, how the induced EMF is produced in the closed circuit. So, depending upon that, Faraday's law states that induced EMF in any closed conducting circuit is equal to the time rate of change of magnetic flux linkage factor and by the circuit, and it is given by V EMF is equal to minus d lambda by dt, which is equal to minus n into d psi by dt. Right? Lambda be the magnetic flux linkage factor and psi be the flux through each turn. Next, define motional EMF. So, in a conducting loop moving with a uniform velocity u as consisting of a large number of free electrons, the EMF induced in the loop, such type of EMF is called as motional EMF or flux cutting EMF because it is due to motional action. So, depending upon this Faraday's law, we will come to know two types of EMFs. One is a transformer EMF and is related to stationary loops, whereas motional EMF is related to the moving loops. Right? So, in a conducting loop moving with uniform velocity u as consisting of a large number of free electrons and the EMF induced in that particular loop, such type of EMF is called motional EMF or flux cutting EMF because it is produced due to motional action. Right? Next, define Ampere's force law. So, Ampere's force law states that the force of attraction or repulsion between two wires carrying currents is proportional to their lengths and the intensities of current passing through them. Right? Ampere's force law. It states that the force of attraction or repulsion between two wires carrying currents is proportional to their lengths and the intensities, magnetic field intensities of current which is passing through between them is called as Ampere's force law. So, now to know the motional EMF, we will be considering here a conducting loops. In a conducting loop moving with uniform velocity, if that stationary object is moving with a velocity u and it is consisting of a large number of free electrons, and inside the circuit there exists an induced EMF. Such type of EMF is called motional EMF. It is also called as flux cutting EMF, and it is produced because why it is called so motional EMF means because it is produced due to motional action. Then Ampere's force law. So to define this Ampere's force law, a statement, it states that the force of attraction or repulsion between two wires carrying currents is directly proportional to their lengths and the intensities of the current passing through between them. Is called as Ampere's force law. Then define Ampere's force law. So in magnetostatics, the force of attraction or repulsion between two current carrying wires and is often called as Ampere's force law. It's often called as Ampere's force law. It is obtained between two current elements L1 and L2. Then mu1, mu0, I1, I2, dl1 into dl2 by 4 pi epsilon naught R12 square into AR12. Okay, so this is what the Ampere's force law can be defined. Magnetostatics, the force of attraction or repulsion between the two current carrying wires is often called as Ampere's force law. Then define electric dipole moment. So the electric dipole moment is a measure of the separation of positive and negative electrical charges within a system. That is a measure of the system's overall polarity is given by electric dipole moment. Means suppose if you consider 2 point charges as q and minus q plus q, and the distance between these two are represented with small d, and the electric dipole moment can be defined as q into d. Q be the charge and d be the distance between two poles. The electric dipole moment is a measure of the separation of a positive and negative electric charges within a system, and that is a measure of the system's overall polarity is given by electric dipole moment. Right? Now to define this Ampere's force law, we need to consider two current carrying wires, and in magnetostatics the force of attraction or repulsion between the two current carrying wires is called as Ampere's force law. Okay. Then what we have what we have learned in this particular lecture is the definitions related to all the fundamentals related to the magnetostatic fields. So firstly we have learned Biot-Savart's law, then after that Ampere's circuit law. So these are the two important laws which are governing in the magnetostatics, where Biot-Savart's law deals us with the differential component of magnetic field intensity is directly proportional to the current element IDL and the sinusoidal angle between the current element on the point P. And it is inversely proportional to the square of the distance between two, means those 2 points are current element and the point P, where we are going to evaluate magnetic field intensity. Then after that, we have learned Ampere's circuit law. The closed line integral of H around any closed path is same as that of the net current enclosed by the path. And also we have learned Ampere's force law, then Lorentz force law, then Lenz law, then after that Faraday's law. Induced EMF in any closed conducting circuit is directly proportional to the time rate of decrease of magnetic flux linkage factor, that is VEMF is equal to minus d psi by dt. Then after that, depending upon this transformer EMF, we have learned two types of EMFs. One is transformer EMF, that is related to the stationary loops, and another one is motional EMF. Okay, so these are all the fundamentals which we are going to learn in this particular module 2 as magnetostatics.
Like, share and subscribe. Hit the bell icon for more updates.